Wastewater comes from many things we do every day. It flows from our homes, our offices, our schools, and our hospitals, even factories, hotels, and shopping malls. The amount of wastewater produced changes depending on where it comes from. For example, a regular home might produce about 100 gallons of wastewater per person per day. A hospital, on the other hand, can produce a lot more, sometimes up to 200 gallons per bed per day. This continuous flow of water needs to be collected and sent to a central treatment plant. If we don't do this, there will be major environmental damage and a direct threat to people's health. The importance of treating this water cannot be overstated. Untreated wastewater, if it goes directly into rivers, lakes, or oceans, will use up the dissolved oxygen that aquatic creatures need. This will lead to fish dying and ecosystems being destroyed. It also carries a dangerous load of disease-causing microbes, like bacteria, viruses, and parasites. These can pollute our drinking water sources and cause widespread disease. In addition, nutrients can cause harmful algae to grow. Chemicals introduce persistent toxins into the environment. That's why regular and effective wastewater treatment is a basic cornerstone of modern sanitation. It's a crucial process that protects our natural resources and keeps our communities healthy. The journey of wastewater doesn't end when it disappears down the drain. It starts its complicated journey through a huge network of underground pipes, which we call the sewer system. This network is very carefully designed to move raw wastewater using gravity. With the help of pumping stations, these stations are amazing pieces of engineering built to copy and speed up nature's cleaning processes. They are the final stop where dirty liquid turns into clean, safe water. Understanding this journey is the first step to truly appreciating the science and engineering needed to manage this public service. The main goal of a wastewater treatment plant is to remove pollutants until the water is safe enough to be put back into nature or reused. This process isn't just about filtering out solid stuff. It involves physical steps, chemical steps, and biological steps. The successful running of these plants is essential for completing the water cycle in our communities. This commitment to treatment is a clear sign of a developed and environmentally aware community. Okay. Raw wastewater is a complex mix. Raw wastewater is a complex mix. It has a wide range of stuff in it that we need to understand so we can treat it. One of the most important things in it is solids. Human waste food, bits, sand, gravel. We split them up by how they look. Suspended solids and dissolved solids. Some suspended solids are heavy and settle easily when the water is still. Some suspended materials are tiny and hard to get rid of with just simple settling. Another important thing is biochemical oxygen demand, or BOD. BOD measures how much oxygen aerobic bacteria need to break down organic stuff. This is usually measured over 5 days. A high BOD means there's a lot of organic material that can be broken down. A high demand for oxygen can take away the oxygen fish need to live. So, lowering BOD is a main goal in treatment. Wastewater is full of nutrients, nitrogen and phosphorus. Nitrogen is usually ammonia, which is bad for fish. Phosphorus often comes from soaps and human waste. Too much of these causes something called eutrophication. Algae grow super fast. When these big clumps of algae die and break down, they use up a lot of oxygen. This creates dead zones, where water creatures can't live. Wastewater can also carry health risks and germs. Harmful bacteria, harmful viruses, harmful protozoa. Getting exposed can lead to sicknesses like cholera, typhoid, and stomach flu. Turning raw wastewater into clean water is a well-organized process. It happens in clear steps. Each step is made to take out certain kinds of pollution and clean the water bit by bit. Flow diagram shown: preliminary treatment, primary treatment, secondary treatment. The first step is called preliminary treatment. The main goal of the preliminary stage is to remove big, rough, solid materials and trash. This is done using tools like bar screens, metal bars that catch trash, plastic bottles, fabrics, wood, stones. We also use grit chambers to slow down the water flow. This lets heavy, non-living things like sand and gravel settle down. This step is super important to protect pumps and pipes from breaking and getting clogged. After preliminary treatment, the wastewater flows to the primary treatment stage. The water goes to large primary settling tanks. The flow speed drops a lot, which creates calm conditions for things to separate by gravity. Sludge settles to the bottom. Lighter greases and oils float to the top, and we remove them. Primary treatment removes about 50 to 70% of suspended solids and 30 to 40% of BOD. But it's not good at removing dissolved organic matter. The most important stage for removing organic matter: secondary treatment. The secondary stage is a biological process that uses tiny living things. The most common way is activated sludge. Wastewater from primary settling mixes with a microbe culture in an aerated tank. The microbes eat the pollutants and turn them into carbon dioxide and water. Section 4. The heart of the matter. Explaining the activated sludge process. The activated sludge process is the cornerstone of secondary biological wastewater treatment. It relies on a carefully managed ecosystem of tiny organisms to clean the water. The basic idea is to create a perfect environment for aerobic bacteria and other tiny organisms. By giving them a steady supply of oxygen and mixing the wastewater with a lot of these tiny organisms, the natural breakdown process speeds up. The bacteria eat the dissolved organic stuff, which we measure as BOD, and turn it into carbon dioxide, water, and new bacterial cells. This biological change turns dirty water into cleaner, treated water. The system has three main parts: the aeration tank, the secondary clarifier, the RAS, return activated sludge, system, and WAS, waste activated sludge, lines. The aeration tank, wastewater from the primary treatment mixes with the recycled activated sludge. Air or oxygen is constantly pumped in to keep the dissolved oxygen levels up. Constant mixing keeps the tiny organisms floating and in contact with the organic material. The tank size and amount of aeration are designed to give enough time and oxygen. After a few hours, the mix flows into the secondary clarifier. In this big tank, the solid clumps settle to the bottom. Above them, a layer of clear treated water gathers. The clear liquid on top is drawn off. How well the solids separate determines the quality of the treatment. A well-working clarifier produces clean water with very low cloudiness. A key part of how it works: the RAS, or return activated sludge system. Some of the sludge is pumped back to the front of the aeration tank. This recycling makes sure there's a high amount of active tiny organisms. To prevent too much buildup, we regularly remove some of the sludge. This is WAS. Managing the RAS and WAS amounts is important for the plant operator to control how well the system works. Section 5. Beyond the basics. Advanced nutrient removal. Secondary treatment is super good at taking out organic stuff and floating bits, but it often leaves a lot of nutrients behind, especially nitrogen and phosphorus. To keep sensitive waters safe from too much algae growth, many treatment plants add special steps for advanced nutrient removal. Nitrogen removal usually happens in a two-step biological process: nitrification and denitrification. The first step, nitrification, needs air, usually in the main aeration tank or a special part of it. Nitrification needs enough oxygen and a long sludge age, SRT, for the slow-growing bacteria. Nitrifying bacteria change harmful ammonia into nitrite, then into nitrate. The second step, denitrification, changes nitrate into harmless nitrogen gas, which goes into the air. This is done by bacteria that love places with no dissolved oxygen but with nitrates. A special anoxic zone is often made before the main aerobic area. In this zone, denitrifying bacteria use nitrate to break down organic matter. The result? Nitrogen is removed, and some organic stuff is removed too. This biological process is a good, sustainable way to remove nitrogen. Phosphorus can be removed biologically or chemically. The biological way, called EBPR, uses special bugs called PAOs. This process cycles sludge through anaerobic zones, no oxygen, no nitrates, and then aerobic zones. In the anaerobic zone, PAOs let go of stored phosphorus to get energy to soak up simple organic compounds. When they enter the next aerobic zone, PAOs take in extra phosphorus and store it inside their cells. The alternative is chemical phosphorus removal. This means adding metal salts like ferric chloride, aluminum sulfate, which is alum, or lime. These chemicals react with the dissolved phosphate to form a solid that settles out. This reaction, called precipitation, changes the dissolved phosphorus into tiny solid pieces that won't dissolve. These solid pieces can then be taken out by letting them settle in primary or secondary clarifiers, or by filtering them out. Chemical removal works well, but it makes more sludge and costs money for chemicals all the time. Often, we use a mix of biological and chemical methods to get phosphorus levels really low. Also, there are toxic things from industrial waste and household chemicals, like heavy metals such as mercury and lead, pesticides, and man-made organic compounds. These things are harmful, and getting rid of them or making them safe is a key part of treating wastewater completely. Conclusion. This issue is super serious. We really need to do something about it. Section 6. Dealing with challenges, common operational problems and solutions. Even well-designed wastewater treatment plants can face operational problems that affect their performance. One of the most common problems in the activated sludge process is sludge bulking. This happens when the sludge in the secondary clarifier doesn't settle well. It forms a thin, low-density sludge blanket that can flow over the weirs with the treated effluent, making the water quality worse. The main reason is often too much filamentous bacteria growing. They form a web-like structure that stops the sludge clumps from sticking together. The solution: increase the dissolved oxygen level in the aeration tank. Another solution: adjust the RAS rate to change the sludge age, a temporary solution in some cases, an oxidant dose, like chlorine, to control filamentous bacteria. Another problem: foam forming on the surface of aeration tanks and clarifiers. Light white foam often means new sludge and a young sludge age. Thick dark foam is usually caused by certain types of filamentous bacteria, like nocardia, which grow on oils and grease. Solutions for foam: treat the root cause. Reduce the amount of wasted activated sludge, WWAS, to increase sludge age. Use surface water spray systems to physically break up the foam. Add anti-foam chemicals as a temporary fix. Poor settling in the secondary clarifier can happen for another reason. A high MLSS concentration can overwhelm the tank, leading to a high sludge blanket and solids escaping. This is a hydraulic or solids loading problem. Solution: reduce the solids inventory by increasing the WAS rate. The problem of tiny scattered clumps leads to cloudy effluent even when the sludge blanket has settled. This is often caused by old sludge age or too much disturbance. Solution: adjust the WAS rate to get healthy, younger sludge, and make sure the tank's inlet and outlet structures are working to reduce turbulence. Bad odors are a constant worry and lead to community complaints. Odors come from anaerobic conditions where organic matter breaks down without oxygen. The result: hydrogen sulfide, which smells like rotten eggs, and other volatile compounds. This can happen in collection systems, primary clarifiers, or sludge treatment areas. The direct solution: improve aeration and prevent anaerobic conditions. Increase air supply in aeration tanks. Reduce sludge retention time in clarifiers. Use odor control technologies like chemical scrubbers or biofilters. Regular cleaning and maintenance to stop odor-causing materials from building up. Section 7. Conclusion: the path to consistent and effective treatment. Turning raw wastewater into clean water is a super advanced multi-step process. It's super important for people's health and keeping our environment safe. First, we screen out big junk in the primary treatment. Then, gravity helps settle things in the primary clarifier. Next is the biological heart, the activated sludge process. We also have advanced nutrient removal systems, which target nitrogen and phosphorus to protect our waterways from too much algae. This whole system shows off amazing engineering and how well biological processes can work together. For things to work well all the time, you need more than just good buildings and pipes. It needs careful and smart management that plans ahead. The main thing is to keep watching everything all the time. We regularly check BOD, COD, total suspended solids, TSS, nutrient levels, pH, and dissolved oxygen. These checks give operators super important information so they can make changes right away. These measurements are like the plant's vital signs, giving us early warnings. A strong monitoring plan is the base for how we control everything. It makes sure the plant runs as well as it possibly can. Making really good treated water has its challenges. Operators need to be ready for problems like sludge bulking, foaming, bad settling, and bad smells. Understanding why these happen and having real solutions helps keep things stable. This all needs technical know-how, experience, and a promise to keep learning new things. This makes sure we safely release water back into nature. Good treatment is a never-ending cycle of running, watching, and making things better. It's a changing process that adjusts to daily and seasonal changes in how much water comes in and what's in it. We always try to make things better, work smarter, and use less energy. We improve the quality of the treated water. We stick to clear rules for how we operate. We react quickly when things go wrong. We keep focusing on the main ideas of treatment. This makes sure we keep protecting our communities and water for everyone in the future.